Hello everybody, welcome back to our channel, Chemistry again. Now we are still at the S2. We are on S2.4, okay, from models to materials. We learn about models of bonding, ionic, covalent, and then we talk about polymerization at last, okay. It is SL and HL, okay. HL is the last part, okay. So how can we decide what is the bonding? We call it a bonding triangle. It's given in the data book. It's a triangle. It is decided by two factors. One is the difference of electronegativity, and the other is average electronegativity. By these two factors, you can mark the compound on the bonding triangle, and from the different position, you can decide whether it is a metallic, ionic, polar covalent, or pure covalent bond. All the things are given in the data booklet. The electronegativity data is also given in the data booklet. Get used to it, okay. For example, position in a bonding triangle, some things are quite funny. For example, okay, the position of a compound in the bonding triangle is determined by the relative contribution of the three bonding types to the alpha wall bond. Okay. First, you have to determine the position of a compound. The compound comes from the electronegativity data, and then from the position, you will have to predict its property, whether it is metallic bond, ionic bond, polar covalent, or covalent. For example, the electronegativity of H is 2.2 and E is 0.9 and Cl is 3.2. Okay. For pure atom or molecules, okay, just as that, right? So the difference of electronegativity is 0. So the vertical position is 0, so it's on the horizontal axis. So sodium is here, hydrogen is here, chlorine gas is here. Okay, and you can see Na is a metallic, H2, Cl2 is a covalent. And now you're on a binary compound, two things joined together. For example, sodium chloride and hydrogen chloride. Okay. For the sodium chloride, okay, data book again. Average electronegativity is 2.1, and the difference in electronegativity is 2.3. So 2.1, 2.3. Wow, ionic. Okay. Even on the right hand side, there's a percentage of ionic there. You don't need to calculate, just copy it. It's okay. HCl average electronegativity 2.7, and the difference in electronegativity is 1, so it is a 2.7 and 1.0. Oh, it's polar covalent, okay, for HCl. So electronegativity data is given in the data booklet. Get used to it. Out of IBDP common calculation, you can just copy it from this slide from the data booklet. You'll see it very soon. No need to calculate, just copy it, okay. For example, where can I find is in the number line, okay, first ionization, electronegativity, and also electronegativity. Don't miss it, okay, I'm number line, okay. So you got the electronegativity, and for the notebook, guys, they don't form bonding, so they have the electronegativity is not available. And you can see the bonding triangle is said clearly, although not very good in the format. This one should be on the left, okay, to make it up, okay. And average electronegativity is here. You can see the percentage of covalent, percentage of ionic. You don't need to calculate it, just copy it by different heights, okay. And alloy, okay, remember we learned about metal bond, right? Electrons is symmetric, so they can slide through each other, no difference, okay. But if alloy are mixtures of metal and other metals, or non-metal, we call it doping, okay, they have enhanced property. We make it out, of course, it's enhanced property. We want to make something that's useful, right? So with the addition of other elements B, okay, the compound metal A becomes an alloy. The symmetry of the metal lattice is broken. No more symmetry, so they can't slide each other easily. The regular arrangement of metal ions is broken. The bonding between metal ions and alloy becomes non-directional. So layers of ions cannot slide through each other so easily. So it's stronger than the original one. And also alloy is generally less available and ductile. They can slide each other. Okay. So common example is bronze, brass, and stainless. You want it to be not so easy to be available and ductile, then make it an alloy, right? Polymer is another thing. Monomer and polymer. Polymer are large molecule, okay, macromolecule, forming by repeating units called monomer. The monomer bonds together and form a long chain of covalent bond atom. For example, cellulose is a common natural polymer in organisms. And plastic, okay, man-made. Plastic is a common synthetic polymer. There's a good side, but the good side becomes a bad side actually. The carbon atoms in plastic, okay, bond with each other to form a long chain of atoms. Okay. The carbon atom also bond with hydrogen, oxygen, nitrogen, chlorine, sulfur, in different kinds of plastic. Okay, as a mass number of carbon just travels, so plastic is light. Okay? Excellent one. Okay, and plastic has a long chain of strongly bonded carbon, such plastic is chemically stable. Okay? So we can break it easily. So we stay in the dump field for a long time. Okay, so it's the best side too. Plastic can also have a low thermal and electrical contact with low free energy, so it can be used as thermal and electrical insulator. So how to make polymer? For example, plastic is because additional polymerization is breaking the double bond, and break that one double bond becomes two single bonds, and then join the isomer together. That's to be additional polymer. So you must have a double bond alkane. So monomer identical alkane to form polymer. Polymer is a long chain of repeating units formed by breaking the double bond of alkane. If the monomer only have one CC double bond, so after forming the polymer does not have CC double bond. Right? Yeah, so it's not alkane. And the CC double bond in the monomer makes it more reactive than the polymer form. The polymer is stable. Okay. And backward engineering. You're required to find out the structure of monomer from the polymer. Okay, so first find out the repeating unit, and then replace the one double CC bond with CC double bond, and you can find out the monomer. So easy, right? Additional high level is a little bit complicated, but not that hard. Okay? It's still a polymerization, but it's by condensation. Okay, very biological one. Okay? For example, carboxyl group and the hydroxyl group join together by condensation and then forming a bond if it has two carboxyl and two hydroxyl, so each of them can form two bonds, right? So the bonding can continuous, becomes a polymer, right? So it is formed by two different things. Okay, each have two carboxyl group and or two hydroxyl group. Okay? And of course, it can be alternate. Okay, one thing having both the carboxyl and hydroxyl group. Okay, they can still form a chain with two condensation, okay, of water. Of course, we can form a polyamide. Okay? So it's the carboxyl group and the amide group, NH2 joined together to form the water. Of course, it has to be bi, right? Two amide group and two carboxyl group again in one molecule, and then we call it forming a polyamide. Of course, it can be alternating. One molecule has a carboxyl group and amide group together. Okay, one on left and one on right, so it can form polymer. And nowadays we are thinking about how to get rid of the carbon dioxide. Okay? So we are thinking about maybe we can use carbon dioxide to form some polymer, and then make the carbon dioxide useful and make it less in the atmosphere, decrease the greenhouse effects. Okay, so it's the way to double bond, join together, and then forming a polymer. Right? We want to do this ring, make it useful, and also decrease the atmospheric carbon dioxide. We are still working on it. I hope 10 years or 5 years we have heard more good news on it. Okay? So that's it. Okay, we talk about how to model habits. Okay, triangle and then polymerization, and some SL and some HL level. Yeah, I hope it help you to prepare for the IB. Okay. See you next week. Bye.